Okay, now in chapter 7, we come to talk about some of the periodic properties of the elements. In chapter 6, we talked about electron configurations and valence electrons and light. We had some sense of the electronic structure of the atom. And now we talk about some of the repeating properties of atoms in the same column of the periodic table, and trends in atomic size, in the energies associated with giving an electron to an atom or taking an electron away from an atom. And in order to talk about any of those, we first have to return to the development of the periodic table itself. Now, you may be very familiar with this scientist on the left, Dmitri Mendeleev. He gets a lot of credit for the development of the periodic table that we use today, which is essentially his table simply expanded upon. And so here we see the elements arranged into different columns and rows known as periods. And they're known as periods to some degree because scientists noticed that there were periodic repeats in terms of similar properties of elements. So as you increase in atomic weight, you would get to, at one point you got to oxygen, but then as you kept going through the elements, eventually you would hit sulfur, and sulfur had very similar properties to oxygen. And then you kept going and you would come to selenium, and selenium had very similar properties to oxygen as well. And so they saw this kind of periodic repeating of properties. However, a scientist who doesn't get a lot of credit is a German scientist by the name of Lothar Meyer. He actually had published a version of the periodic table before Mendeleev in 1864. Mendeleev's was published in 1869. And then he updated it in 1870 with a version of the table which looked almost identical to Mendeleev's table. And so both of these scientists deserve credit for arranging the periodic table that we use today. Now, what they had noticed when they arranged their tables was that elements in the same group have similar properties, as we just mentioned. But having or building on our discussion from chapter 6 with valence electrons, we can now understand why elements have similar properties in the same column. And that's because they have the same number of valence electrons. So if we look at those three examples of oxygen, sulfur, and selenium that I mentioned just a moment ago, if we go through and write out their condensed electron configurations where the noble gas in parentheses represents then the core electrons for oxygen and sulfur, then we have for oxygen 2s2, 2p4, that's 6 valence electrons. Sulfur has 3s2, 3p4, it has 6 valence electrons, and then selenium has 4s2, 3d10, 4p4, but the d electrons, remember, if they're full, are core electrons. So selenium also has only 6 valence electrons. So all three of these elements have the same number of valence electrons. And thus they have similar chemical properties because of the fundamental reality that only valence electrons are involved in chemical reactions. And so if an element has the same number of valence electrons as another element, then we could expect that it would behave similarly because it's only the valence electrons that are involved in any of the chemical reactions. This is 99% true. There are rare cases in chemistry where we can encounter uses of core electrons for various purposes, but for all of our purposes, only valence electrons are involved in chemical reactions. So let's take a look at an example here. This is a reaction we've seen previously. It's a redox reaction from chapter 4. Calcium is reacting with oxygen, and the calcium starts out with a 0 oxidation state or a 0 oxidation number, but then it ends up in the ionic compound calcium oxide, and it's 2+ here. And so calcium goes from 0 to +2 in terms of its oxidation number and is thus oxidized. It loses 2 electrons. Oxygen, on the other hand, starts at 0 since it's in its elemental form, but then ends up as 2- in the ionic compound, and thus it's been reduced. Goes from 0 to -2, it's gained 2 electrons. So if we're looking at valence electrons, what we can do first is we can just draw out the electron configurations for both of these starting materials. Calcium is just argon in parentheses, and then 4s2, it has 2 valence electrons. Oxygen, we've seen before, helium, and then 2s2, 2p4, it has 6 valence electrons. But where do the electrons actually go when they react to form calcium oxide? This is where it's helpful to be able to draw the electron configurations for ions. So what about calcium 2+? How do we draw the electron configuration for that? What happens to the electrons? Well, calcium essentially loses 2 electrons compared to its neutral form. And so we simply draw the electron configuration of calcium minus 2 electrons. Well, those 2 electrons are lost as the valence electrons. So it loses its 2 electrons in the 4s orbital. And we're left then with just the electrons in the argon configuration. And so we can either draw it with 4s0, or really anything that's got 0 electrons in it, we can simply leave off. And so we can write it as argon in brackets, or the condensed version of argon, which is neon in brackets, 3s2, 3p6. On the other hand, what about oxygen? So that's for calcium losing the electrons. What about the oxide, the O2 minus? Well, oxygen has an electron configuration of helium in brackets, then 2s2, 2p4. If we add 2 electrons to that, if it gains 2 electrons, those 2 electrons go into the p orbitals, because that's the available space. And so we end up then with an electron configuration of helium, 2s2, 2p6, or simply neon in brackets. So it would be helpful perhaps to have some really clarified rules for how we write electron configurations for ions. This is really helpful in not only keeping track of the electrons, but also where the electrons go in terms of orbitals. Let's start with anions. Those are the cases where we have extra electrons and a negative charge. Again, we're only going to look at monatomic ions. We're not going to look at polyatomic ions here, just monatomic ions. And so the first process in this case is just write the normal electron configuration for the neutral atom, and then add the number of electrons that are equal to the charge to the end of the configuration. So what does this look like? Well, let's do maybe N3 minus as an example. But first, we would just write the electron configuration for nitrogen. That's helium, 2s2, 2p3. And then we're going to add the number of electrons equal to the charge. So we add 3 electrons to it to give it a 3 minus charge. If I add 3 electrons to it, those 3 go at the end into the p orbitals, and I end up with 1s2, 2s2, 2p6. Or again, just neon in brackets. So that's fairly simple for anions. Can it be more complicated? Well, cations are only slightly more complicated, but not by much. So cations are those where we're missing electrons now. We have a positive charge. So our electron configuration is going to have less electrons in it than the neutral atom. But the process is still very straightforward. We write the normal electron configuration for the neutral atom. And then we subtract the number of electrons equal to the charge from the configuration, beginning with the electrons in the highest energy level. What do I mean by that exactly? In the highest energy level. Well, the explanation for that is in a cation, so once we've started to lose electrons, in a cation, the d orbitals, if there are any present, are actually lower in energy than the s orbital of the next energy level. Remember when we drew out the electron configuration for neutral atoms, the d orbital of one level was actually slightly higher in energy than the s orbital of the next energy level. Well, in cations, that no longer becomes true. Those switch back again. So the d orbital is now lower in energy than the s of the next energy level. And as a result, we lose electrons from the highest energy level first. So let's take gallium 3+ as an example. So gallium itself has a condensed electron configuration of argon, then 4s2, 3d10, 4p1. because because we're forming a cation, the d orbitals here, even though they're written out in the neutral atom as being higher in energy than the 4s, in a cation, they're actually lower in energy. And so when I go to when I have to go lose 3 electrons from the neutral atom's electron configuration, I take them from the 4 energy level first, and I don't take them from the 3 energy level. So I'll still start with the highest energy orbital. So first I take 1 electron from the p, that empties all of the electrons in the p orbital. I still need to take 2 more, because I have to lose 3 electrons to get to a 3+ charge. So I take those 2 from the 4s orbital. And that leaves me then with the argon and then 3d10, not argon 4s2 3d8, where I would have taken them from the d orbitals. Remember, the d are lower in energy than the next s when we're dealing with a cation. Let's do maybe another example, one that starts with d orbital. So iron 2+. So in this case, iron starts out as argon 4s2 3d6. And I need to lose 2 electrons. In a cation, the d orbital is lower than the next energy level's s orbital. So I take the 2 electrons from the s orbital and not from the d orbital. So I end up with argon 3d6 and not argon 4s2 3d4. So that's how I would do electron configurations for ions. Let's do a couple problems together. So what's the electron configuration of lead? This is Pb in lead carbonate. Well, first let's just identify what the charge is on lead, and we can write out the normal electron configuration for lead, and then we can deal with subtracting those electrons. So first, it's lead 2+. The reason I know that is because the carbonate ion is 2-, so to be balanced, lead must be 2+. Now, that essentially just means that I have to take the normal lead and subtract 2 electrons from it, from its electron configuration. Now, normal electron configuration for lead is just xenon, and then I list all of the things then in order from there. It's 6s2, and then we're at the point where we have to insert the f orbital, so then it's 4f, 14, 5d10, and then 6p2. And I have to subtract 2 electrons from this. Well, I'm going to start by taking those 2 electrons from the highest energy level. So I'm not going to touch the d electrons. I'm not going to touch the f electrons. Those are at the 5 and the 4 energy levels. I'm going to take the electrons from the 6 energy level. And I'll start with the highest energy there, which is the p. The p orbitals are higher in energy than the s. So I will take 2 electrons then from the p. That empties the 6p orbitals. And so I just have xenon, 6s2, 4f14, 5d10. Okay, then what's the electron configuration of nitrogen? Oops, that's a slight mistake on my part. Selenium is actually what I'm looking for here, not nitrogen. It's a slight adjustment from an earlier problem. But in aluminum selenate here, so we've got aluminum with selenium. What's the electron configuration of selenium? First, we have to figure out what the charge on selenium is. Well, it's in that column with oxygen. So just looking at the periodic table, I can predict it'll be a 2- charge. And then essentially I can just write from there, it's selenium plus 2 electrons. So I write out the electron configuration for selenium. That's argon in parentheses 4s2, 3d10, 4p4. I have to add 2 electrons to it. Those just go into the end orbital there. And I get to argon 4s2, 3d10, 4p6, or just that's the same configuration as krypton. So that's how I can write electron configurations for ions in addition to just the electron configurations for neutral atoms.